Okay, so today we're going to look at elastic collisions specifically. In the previous video we looked at all kinds of collisions, but now we just want to look at a special case, which is when the two carts bounce off of each other. Now the first thing I want you to notice for an elastic collision, and to make this elastic there's magnets on these sides that repel each other. The first thing I want you to notice is that when they hit, they don't make a lot of sound. And in fact, they don't actually touch because the magnets are repelling. Now, if I were to turn these around, and make them collide, it makes a sound. That sound is caused by vibrations that occur when the cars collide. Those vibrations are internal energy. Notice when I do it this way, they don't really make a sound when they collide. So there's none of the kinetic energy is converted into internal energy. And that's what makes an elastic collision elastic. The kinetic energy is conserved. Now we already know that in any collision, momentum is conserved. The total momentum before the collision and the total momentum after the collision are the same. With an elastic collision, what is also true, the total kinetic energy before the collision and the total kinetic energy after the collision is also the same. Now, after the video I'll show you how this works out mathematically, but what this means is during the collision or after the collision, the velocity of car B relative to car A will be the same as the velocity of car A relative to car B before the collision. So let me show you that. So I'm going to push car A towards car B. We'll leave car B not moving. And let's just say I push car A at 1 meter per second. And you'll notice car A stops, car B takes off at 1 meter per second. So prior to the collision, car A had a velocity this way of 1 meter per second relative to car B. After the collision, car B had a velocity this way of 1 meter per second relative to car A. Let me show you that again. All right, car B takes off at the same speed that car A had before. Now, if I push them toward each other, both at 1 meter per second, they're moving at 2 meters per second relative to each other before the collision. And notice, after the collision, they move backwards at the same speed. So they're also moving at 2 meters per second relative to each other after they collide. All right, now let's try some other examples here. I'm going to double the mass of cart A. I'm going to push it toward cart B. After this collision, cart A will keep moving a little bit, but car B will take off a little bit faster than it did before. So let's just say that car A keeps moving forward at 1/3 of a meter per second. Car B is going to take off at 1 1/3 meters per second. All right, so before the collision, car A was moving this way at 1 meter per second, which was 1 meter per second relative to this car. After the collision, this car took off at 1 1/3. This car kept moving at 1/3. All right, and we can play around with that. I can add more mass to cart A. So cart A won't slow down as much. Car B will take off faster. So before the collision, 1 meter, this car was 1 meter per second relative to this car. After the collision, this car was 1 meter per second relative to this car. All right. I could show you more examples of that, but I think that's probably good enough to make the point.